Good afternoon. My name is Fabio Gonzalez, and I'll be presenting to you the Chapter 8 overview alongside my partner Donovan. So we're going to go ahead and start with concentration units and dilutions. So concentration units are expressed as either of the following. So they can be expressed as mass-to-mass ratios, which is represented as milligrams of the solute over kilograms of the solution, so milligrams per kilogram, or they can be expressed as parts per million. So then moving on to the second form, being mass to volume ratios, an example would be milligrams per liter. And then the third is in terms of molarity, and this involves putting the moles, the number of moles of the solute over the volume of the solution, where the volume of the solution usually represented as liters. And this is expressed with the uppercase letter M. So let's say we have 50 grams of sodium chloride in a 1 liter solution, and we want to express it in the three different forms. So starting with mass to mass ratios, we can show this as 50 grams over a kilogram, so it would be 50 grams of the solute per kilogram of solution, or 5 times 10 to the fourth milligrams per kilogram, converting the 50 grams to milligrams. Next, we could express it as mass to volume, and we would write this down as 50 grams per liter, or 5 times 10 to the fourth milligrams per liter, also converting grams to milligrams. And then in terms of molarity, we would have to get the 50 grams and convert it to moles. To do this, we would multiply the 50 grams by 1 mole over 58.44 grams, being its molar mass, and this would give us 0.86 moles of the solute, being of sodium chloride. Then we'd put this all over 1, since the volume of this solution is 1 liter, and this would give us 0.86 molar sodium chloride for the concentration. Moving on to dilutions. Dilutions involve adding solvent to decrease solute concentration, and usually we just add water. So let's say we start with 1 liter of 0.80 molar sodium chloride, so that would be the concentration of the solute, but we want a 100 milliliter solution of 0.35 sodium chloride, with 0.35 being the concentration in the second solution. So how would this be done? So we're going to use the equation for dilutions, which is the initial solute concentration times the initial volume of the solution equals the final concentration of the solute times the final volume of the solution. So we have all the variables except for the initial volume of the solution, which is the amount of solution that we need to add to the total 100 milliliter solution to get that desired concentration. So when we go ahead and plug in the numbers, being 35 molar sodium chloride times 100 milliliters all over 0.80 molar sodium chloride, that gives us 43.75 milliliters of the solution. So this means that we need to get 43.75 milliliters of the original sodium chloride solution and add 56.25 milliliters of water to get an 100 milliliter solution with a concentration of 0.35 molar sodium chloride. Alright, so let's go ahead and move on to using Beer's law and absorbance values to find the concentration of an unknown solution. So first, to find the concentration, we're going to have to make dilutions of a standard solution, which is going to have a known concentration of the unknown solute, and then we're going to measure the absorbance of all the dilutions to make a calibration curve, and keep in mind the calibration curve should be linear. And then we're going to find the slope, and to do this you can use a program such as Excel to find the slope-intercept form. And then knowing that Beer's law is absorbance equals molar absorptivity times path length times concentration, we know that the slope is going to be molar absorptivity times path length, since the graph shows absorbance as the y-axis and concentration of the solute as the x-axis. So knowing this, we only need to find one more variable, being absorbance. So you can go ahead and use laboratory tools to find the absorbance, and then you just go ahead and plug and chug and isolate for concentration. So that would mean that the concentration equals, let's say we used the dilution with the absorbance value of 0.25, it would be concentration of the solute equals 0.25 all over 0.2543, and the 0.2543 is a molar absorptivity times path length, and that's going to give us a concentration of the solute in that dilution being 0.98 micrograms of the unknown solute per milliliter of solution. Let's go ahead and move on to writing chemical equations for aqueous solutions, identifying between electrolytes and non-electrolytes, as well as between weak and strong electrolytes, and identifying Bronsted-Lowry acids and bases. So the chemical equations and the identifying between strong and weak electrolytes as well as non-electrolytes is going to tie in with each other. they're going to intertwine. So starting with writing a molecular equation, so we're going to go ahead and write a molecular equation for sucrose dissolving in water. So we have 12 atoms of carbon, 22 atoms of hydrogen, and 11 atoms of oxygen for the sucrose molecule, and it's going to be in solid form to begin with, and it's going to react with water in liquid form, and then we're going to have a reversible reaction since although it does dissolve in water, it can revert back to its solid form. So, and when the chemical reaction does occur and sucrose dissolves, we observe how the sucrose molecule itself does not break apart into its individual atoms. It actually remains intact and instead just changes form from solid to aqueous form, and the water stays the same. So writing down its net equation, we go ahead and remove the water since it does not change. And then this intertwines with electrolytes since we see how it does not dissolve into ions. So this means that it's a non-electrolyte. It will dissolve, but it will only dissolve into its individual molecules, but the molecules themselves won't dissociate. And then moving on to ionic equations, let's go ahead and write the overall ionic equation for potassium bromide. So we're going to go ahead and start with the solid form of potassium bromide, KBr, and then have it react with water, H2O, in its liquid form, and the potassium bromide is going to be in its solid form to begin with. And then once it reacts, and also we can see how there's not going to be a reversible reaction, and so when it does react, we get potassium cations with a charge of 1, and it's going to be in aqueous form, and bromide anions in aqueous form as well with a -1 charge. And then we also have the water in liquid form. So in writing the net ionic equation, we go ahead and remove the water since it remains the same throughout the equation, and then we get that potassium bromide in solid form dissolves in water to form the potassium cations and the bromide anions. So in these equations, there's not a reversible reaction since it dissolves almost completely, meaning that it's a strong electrolyte. So moving on to how we distinguish between strong and weak electrolytes and non-electrolytes, let's remember that ion movement is what results in high conductivity of electricity. This means the more a ionic compound dissolves, the higher conductivity it will have, and therefore the stronger it'll be as an electrolyte. So this is why, for example, the potassium bromide was a strong electrolyte. It dissolved almost completely, so it conducted electricity well. Another example of a strong electrolyte would be sodium chloride, which also dissolves almost completely. And then an example for some weak electrolytes would be like hydrogen fluoride and ammonia, since both of those do not dissolve completely and therefore are weak electrolytes. And then some examples for non-electrolytes would be molecules like sucrose and glucose, which only dissociate into their individual molecules but don't dissociate into ions. So moving on to identifying Bronsted-Lowry acids and bases. Acids are those which give protons away, and these usually consist of highly electronegative atoms bonded to hydrogen. So with highly electronegative atoms being some atoms such as fluoride atoms and chloride atoms, which have high electronegativity values. So since those atoms are very electronegative, the bonds between them and the hydrogens are really easy to break. And when they do break, the hydrogens are given off as protons. Moving on to bases. Bases accept protons, and they are typically hydroxides. And a key feature in identifying a basis is that they have lone pairs of electrons. And these lone pairs of electrons are negatively charged since they're electrons, and they are the ones that attract the protons from acids, or the protons that acids give off. So strong acids and bases dissolve completely, whereas weak acids and bases do not. And this is similar to electrolytes. And this is what separates strong acids and bases to weak acids and bases. Also, strong acids and bases tend to be highly soluble in water. And then some examples of common strong acids are found in the bottom right of the presentation slide.
Now we will be discussing titration calculations and solubility rules. First off, what is titration? Titration is a way of determining the acid or base concentration in a solution by slowly adding one solution of known concentration to a solution of a known volume but unknown concentration. For our first example, 24.7 milliliters of a HCl solution is completely neutralized by 35.8 milliliters of a 0.25 molar sodium hydroxide solution. what is the concentration of the original HCl solution? So first we will write out the balanced chemical equation, HCl plus sodium hydroxide, and that gives us H2O plus sodium chloride. So HCl and sodium hydroxide react in a 1-to-1 ratio. Then we start with the molarity of sodium hydroxide, so 0.25 moles of sodium hydroxide per liter times the volume of sodium hydroxide in liters, so 0.0358 liters. Then we can convert to moles of the acid by using the 1-to-1 ratio we found earlier. So 1 mole of HCl over 1 mole of sodium hydroxide. And finally, we divide by the volume of HCl in liters, so times 1 over 0.0247. So this will give us our answer of 0.362 moles per liter. And that sums up how to do titration calculations. Now onto using solubility rules. So the solubility rules allow us to identify compounds that are soluble or insoluble. Soluble compounds dissolve and are aqueous. Insoluble compounds don't dissolve and are solid. So for the first group on this table, group 1 metals are all soluble with no exceptions. The same is for ammonium nitrate, acetate, hydrogen carbonate, chlorate, and perchlorate. They are all soluble with no exceptions. Next are the halogens, which are soluble with the exceptions of silver, lead, or mercury attached to a halogen. Then we have sulfate, which is soluble with the exceptions of silver, lead, calcium, strontium, and barium. Now the next portion of this table displays compounds that are insoluble with some exceptions. So the exceptions that make carbonate soluble are anything in group 1 or ammonium. Then for chromate, the exceptions are anything in group 1 or calcium, magnesium, or ammonium attached to the chromate. And for phosphate and sulfide, whenever we have group 1 metals and ammonium attached to them, that means that it's soluble. And for hydroxide, when it's attached to any group 1 metals or ammonium, calcium, barium, or strontium, then it's soluble. So now we can use the solubility rules to predict the solubility of compounds. For example, we have potassium bromide. So bromine is a halogen which is soluble with the exception of silver, lead, or mercury, which none are attached. Then potassium is a group 1 element which is soluble with no exceptions, so therefore we know that this is soluble and aqueous. Now for the example below that, chlorine is a halogen, but since it's attached to silver, it is insoluble, making the compound a solid. For the next example, we see that nitrate is soluble with no exceptions, so our compound is soluble and aqueous. Now for our last example, we have a double placement reaction. Potassium chloride and lead nitrate react to form potassium nitrate and lead chloride. We then balance the chemical equation by multiplying 2 to potassium chloride on the left and to potassium nitrate on the right. Then we use the solubility rules like before to determine the solubilities of each compound. So potassium chloride, lead nitrate, and potassium nitrate are all aqueous, but lead chloride is insoluble because chlorine is attached to lead, which is an exception that makes the compound insoluble. And that will conclude how to use solubility rules to predict precipitation reactions. Now we will discuss redox reactions and half reactions. So for redox reactions, we are given a balanced chemical equation, and we must identify which substance is being oxidized, which is the oxidizing agent, which substance is being reduced, and which is the reducing agent. So first we find the oxidation numbers. So let's start with aluminum. Because it is one element in its solid state, aluminum will have an oxidation number of 0. F2 is a diatomic atom, so diatomic atoms have an oxidation number of 0. On the other side of the equation, we have aluminum with a 3 plus charge, so the oxidation number is plus 3. And for fluorine, it's a -1 charge, so the oxidation number is -1. Then we must identify which is being oxidized and which is being reduced. So aluminum is being oxidized because it becomes positive when it goes from 0 to plus 3, while fluorine is being reduced from 0 to -1. So the substance being oxidized is aluminum, and the substance being reduced is F2. The oxidizing agent is a substance that is being reduced, so F2, and the reducing agent is what's being oxidized, so aluminum. So that basically explains how we can use oxidation numbers to identify redox reactions, oxidizing agents, and reducing agents. Now on to half reactions. For example, we have zinc reacting with bromate to produce a zinc cation and bromide. So for acidic conditions, we can use hydrogen ions and H2O to balance a half reaction. So for our first half reaction, we have zinc, which becomes a zinc cation with a +2 charge. So to balance that, we just add 2 electrons. And for our next half reaction, we have bromate that becomes bromide. So bromine is already balanced, so we are left to balance the oxygen. And we can do this by adding water to the half reaction. So we add 3 water molecules to the right and 6 hydrogen ions to the left to balance the half reaction. Now we have to balance the charges. So since we have a +5 charge on the left and a -1 charge on the right, we need to add 6 electrons to the side with the higher total charge, so the left. Then we have to balance the number of electrons in both the half reactions. So we multiply our half reaction containing zinc by 3 to get 6 electrons. Now all we have left to do is to add the 2 half reactions together. So the 6 electrons on the left and the right cancel out, and we can bring everything else down. So for our answer, we end up with 3 zinc plus bromate plus 6 hydrogen ions on the left, and 3 zinc ions plus bromide plus a bromide ion plus 3 water molecules on the right. Everything is balanced and the charges are equal on both sides. And that will conclude our Chapter 8 project. Thank you for listening.